Hey everyone, so today we're going to step away from the world that makes sense, our comfortable common sense world, and dive right into the deep end of quantum mechanics. And we're not just talking about weird particles here. We're talking about how, at the tiniest scales you can imagine, logic itself, well, it just breaks. So let's get into it and see how the quantum realm completely flips the script on everything we think we know.
You know, in our day-to-day lives, things are pretty predictable. A baseball player doesn't need to solve a complex physics equation to catch a fly ball, right? They just know where it's going. It's intuitive. That's the classical world we live in. But when you zoom way, way down to the level of electrons and photons, it's a completely different ballgame, literally. Nothing is certain anymore. It's all about probabilities. The rules that work for a baseball, they're totally, completely useless down there. You have to throw out the old rulebook and start fresh.
Okay, so to really get a feel for just how bizarre this gets, we're going to walk through a pretty simple thought experiment. But I want to be clear here. This isn't just some quirky physics puzzle. No, what we're about to see challenges the very rules of logic that we use every single day. All right, let's start in our world, the classical world. Imagine we have some object, and it has a property we'll just call spin. So first, we check proposition A. Is the spin up? And yep, we measure it, we confirm it's true. The spin is up. Got it. Now we go and check a different proposition. B, is the spin right? Now here's the thing. It doesn't even matter what the answer for B is. If I ask you, is it true that either A is true or B is true? Well, of course it is. We already confirmed A was true a second ago, so that or statement has to be true. Makes perfect sense. Simple logic, right?
Okay, now for the mind-bending part. Let's run the exact same test on a quantum particle. We start the same way. We prepare the particle so that proposition A, the spin is up, is definitely true, locked in. But here comes the quantum weirdness. The moment we decide to measure proposition B, is the spin right, the very act of looking at it, of measuring it, fundamentally changes the particle. It's invasive. So let's say we measure B and find out it's false, okay? But now, and this is the crazy part, what if we go back and check A again? Because we disturb the system just by looking at B, the answer for A is no longer a sure thing. It's now a coin toss. It's entirely possible we'll find that A is now false. So, just let that sink in. We started with A being true. We checked B, which was false, and now A is also false. All of a sudden, our rock-solid logical statement, A is true or B is true, is false. The logic we rely on, it just shattered.
I mean, that result is just wild. It's not just me saying it. Look at this quote from physicists Leonard, Susskind, and Friedman. The very foundations of logic are different in quantum physics as well. What they're saying is that it's not just the physics that's different down there. The fundamental rules of if this, then that, the basic true or false system we use to understand everything, it's fundamentally different. Wow.
So that begs a huge question, right? If our basic logic is busted, how on earth do physicists even talk about this reality? Well, they had to build a new toolkit from the ground up. You can think of it like they had to write a brand new operating system for the universe. Let's take a look at the 3 big rules of this new OS.
Rule number 1 is the idea of a quantum state. See, in our world, things are what they are. A car has a specific location. A book is on a specific shelf. But in the quantum world, not so much. A particle doesn't have one single definite property. Instead, it exists in a cloud of possibilities, a state of pure potential. It's described by a mathematical tool called a state vector, which is basically a list of everything it could be. So it's not about what is, it's about what could be.
Okay, rule number 2, the observable. This is what we measure, things like spin or position. But here's the key. They aren't just numbers sitting there waiting for us to find them. In quantum mechanics, an observable is more like a machine. It's an active process. You take that cloud of possibilities, that state vector, and you run it through this measurement machine. And in doing so, the machine actually does something to the state. It's not a passive reading at all.
And that brings us right to the third, and maybe most important rule, measurement. You just can't be a passive bystander in the quantum world. The moment you measure something, you force it to make a choice. That cloud of possibilities we talked about, it collapses into one single definite answer. And this is the part that should really give you pause. When you measure a quantum particle, you're not just discovering a property that was already there. You are literally participating in the creation of that reality. You force it to become real.
Now, when you put these new rules together, that states are just possibilities and that measurement forces a choice, you get something truly bizarre.
something that even Einstein couldn't quite wrap his head around. You get quantum entanglement.
So here's the classic thought experiment. Imagine we create two quantum coins and they're entangled, meaning their fates are linked from the very beginning. We give one to Alice and the other to Bob. Then Alice gets in her spaceship and travels a long way, say 4 light years to the nearest star system, Alpha Centauri. Before she leaves, they synchronize their watches and agree to look at their coins at the exact same moment.
Okay, the moment arrives. Alice, 4 light years away, looks at her coin. Let's say it's heads. The instant she sees that, she knows with absolute 100% certainty that Bob's coin, back on Earth, is tails. Instantly, across trillions of miles. Einstein famously hated this idea, calling it spooky action at a distance. So what's going on here? Did information just travel faster than the speed of light?
The answer, according to quantum mechanics, is no. And the reason why is even stranger than you might think.
See, this is where our classical intuition just completely fails us. We think of two separate coins, but quantum mechanics says that's the wrong way to look at it. No information was sent from Alice to Bob, because there was nothing to send. Their coins were never two different things. From the instant they were created, they were, and always have been, a single quantum system. They're two parts of a single inseparable whole. When Alice measures her part, she's not sending a message, she's simply defining the state of the entire system at once, which includes Bob's part, no matter how far away it is. They were never really separate to begin with.
So let's pull all of this together. Quantum mechanics isn't just giving us a new set of physics equations, it's giving us a completely different framework, a new operating system for reality itself.
So what are the new rules of this OS? Well, for starters, reality isn't a clockwork machine, it's a game of chance. It's fundamentally probabilistic. Second, things don't have definite properties until they're measured. They just exist as a fog of potential. Third, we aren't just passive observers. The act of measuring actually helps create the reality we see. And finally, things that seem totally separate can actually be deeply connected as part of a single, unified system, no matter how much space is between them.
And that leaves us with a huge, lingering question, doesn't it? We walk around in this solid, predictable world where logic works and things make sense. But we now know that all of it is built on this bizarre quantum foundation of pure chance, ghostly connections, and maybes. So if the very bedrock of our universe is this strange, what does that truly say about the world we think we know?